Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to tell you a little bit more about G-orbits. These G-orbits, by the orbit decomposition theorem, they are like the atoms which you can use to build any G-set. So once we have a description of G-orbits, we'll have a complete description of any G-set. And that's what I want to show in this video today, is a complete description of the structure of any G-orbit. Okay, so to start off with, what we need is some version of the notion of homomorphisms for G-sets. So we've looked at the notion for groups, and we need a version for G-sets. In other words, we need a way of comparing two G-sets, and more specifically, a way of saying when are they essentially the same. Okay, so that's what we need. And that notion is encoded in this notion of equivariant maps. Okay, so suppose we have two G-sets, x1 and x2. We want to compare them, so we have a function f from x1 to x2. When do we say this is G-equivariant or a morphism of G-sets? Okay, we say that holds if the following axiom always holds. Okay, so it's basically a compatibility condition with the group action. Okay, so for all group elements little g and elements in the set x in x1, if you let g act on this x, that will give you another element of x1, and then apply f to it to land you in x2. That's the same if you applied f first to this element of x1 to land you in x2, and let the group element act on that to get you another element inside x2. Okay, so another way to read this or to think about this is you can pull this scalar out, okay, and that always holds true. In that case, this is said to be a morphism of G-sets. Okay, so when are two G-sets said to be essentially the same? Okay, that's the notion of an isomorphism, much as we had this notion for groups. If we have such a morphism of G-sets and it's actually bijective, then we'll say it's an isomorphism of G-sets. And the usual notation for that is this one here, x1 is isomorphic to x2 like that. Okay, so let's have a look at a simple example. Okay, in this example here, the group we're going to fix is just a cyclic group with two elements. So it's just the two residue classes, 0 bar and 1 bar. In other words, the even numbers here and the odd numbers here. The G-sets, the sets themselves, xi, there's x1 and x2, will both be the same, R2. Okay, but the point is that the group action will be different. Okay, so the situation we want to look at is where the group of symmetries is given by this group. And what are the symmetries in terms of this R2? So there'll be symmetries acting on R2. Well, the first one looks at reflection about this horizontal axis. And the other one looks at tau2, which is reflection about this vertical axis. Okay, so to give these two G actions, I just need to give you a permutation representation. So homomorphism from G to permutations in R2. Okay, so let me tell you what the two corresponding permutation representations are. So there's one for each I equals 1 and I equals 2. So I just need to tell you where these two group elements go, 0 bar and 1 bar. 0 bar, of course, has to go to the identity group element, so that's just the identity morphism there. And where does 1 bar go? 1 bar just goes to the corresponding reflection. So in x1, it will be this reflection here. x2, it will be this reflection here. Okay, so there are two setups where we look at symmetry. Okay, and they're different. Okay, they're reflections about different lines, but the point is that they're almost the same. Reflection about one line is just as good as reflection about any other line. Okay, the way you study them is the same way. And so, of course, what we want to say in this case is that they actually give isomorphic G-sets. Okay, and that actually does hold. So we've set up the theory nicely so that we can say that actually we have isomorphic G-sets. So as far as the G action is concerned, you can study these the same way. Okay, so let's see how that works. So the way you do it is, well, you need some sort of map from x1 to x2. And of course, the map you will want to exchange this line for this line here. And the easiest way to do that is just to swap the two coordinates. Okay, so I claim that we do have an isomorphism of G-sets, okay, x1 to x2. So it's just a map from x1 to x2, which satisfies this condition here. Okay. So the one that I'm going to pick is it just swaps the two coordinates, so AB gets sent to BA. And then all you have to do to check that it is a morphism of G-sets, or it is G-equivariant, is that this equation holds for all group elements G and elements X inside the set. Okay, so for all elements X inside the set, they're all A comma B. And then we just have to check for all the group elements, and there are only two group elements, 0 bar, which is the identity, and 1 bar. Now if you put 0 bar, which is the identity here would act on this to give you back x, so this is just f of x. And the identity doesn't do anything, so this is also f of x. So actually, when you put in g equals the identity of the group, this is automatically satisfied. So in this case here, the only thing you need to check is the case where this little g is equal to 1 bar. Okay, so we need to check that it doesn't matter whether you let 1 bar act on this AB first and then apply this map f, or you apply the map f first and then 1 bar. So let's have a look at those two results and see whether they are indeed the same. Okay, so here 1 bar acting on AB. So what's the action here? 1 bar. Okay, so you use this permutation representation. 1 bar gets mapped to tau 1. Tau 1 is this reflection here. So use this reflection to map this pair AB to its reflection, which you get by negating the second coordinate, right? You just negate the second coordinate. So A comma B becomes A comma minus B. Let's just erase that. So that's just A comma minus B. Okay, and now you work out what's that. So what's F? You swap these around. So when you swap these around, you get minus BA. Okay, so let's have a look at the second one. F of AB, you swap the A and B, that's what F does, and let 1 bar act on it. Now what's 1 bar acting on this BA? So 1 bar now is acting, and where are you? You're over here inside x2, okay? You're in x2 and you're letting the 1 bar act inside x2. So that action is via tau 2, okay? So action on tau 2. So remember that actions g dot here and action g dot here is different. This is inside x1, this one is inside x2. So we're using the one inside x2 now. And that one, you change the first coordinate to its negative. So here this first coordinate becomes minus b and the other one stays the same. So that equals minus b comma a. And so we do find that these two are indeed equal. So that checks the second equation for the other group element and for all x's inside this domain G set here. And that shows you that this is indeed a morphism of G-sets. It's clearly bijective, so you get an isomorphism of G-sets. So that means that when you want to study the symmetry of this plane represented by reflection about this line here, okay, it's the same as studying the symmetry about reflection about this line here. And the way to go backwards and forwards between the two is using this isomorphism of G-sets where you just swap the two coordinates. And that's exactly what you think ought to happen. Okay, so now we have a way of comparing two G-sets and saying when they are the same. So the next important notion I want to introduce here is the notion of a stabilizer group. Okay, so let's suppose we're in a situation where we talk about symmetry, so X is a G-set. So we have a G-set, and what we can do is for each little element inside our G-set, little x inside big X, we can talk about its stabilizer. Okay, so what's the stabilizer? So we look at the stabilizer in G of X. Sometimes this subscript G is dropped out when it's clear that what the group which is acting is. So it's going to be some set of group elements, okay, some subset of group elements. It's all the little g inside big G such that G dot X equals X. In other words, all the group elements G which don't move X, they stabilize X in that sense, okay, G dot X equals X. So this is just some subset of group elements inside big G, and it turns out it's actually a subgroup, okay? And to do that is, all you need to do is to check the closure axioms, okay? So let's just check some of them. So for example, 1, is that in there? 1 dot x, does it equal x? Yes, 1 dot x equals x, so 1 is inside there. Okay, let's check closure under multiplication. So suppose you have two group elements, G and H, which are inside the stabilizer of X. You need to check that the product also stabilizes X. So GH dot X is equal to X. Okay, so let's see why that's true. So we want to check, does this equal X? Okay, so of course you have the associativity of this group multiplication. So this is G dot H dot X. And now we use the fact that H is a stabilizer, so H doesn't move X. So H dot X is just X. So that's just G dot X. And G is in the stabilizer, so G doesn't move X. So G dot X is also X. Okay, so that checks two of the subgroup axioms. And the third one that you need to check is that it's closed under inverses. And that follows using a similar sort of computation to what we did here. So it's quite a straightforward check of the group axioms, which gives you this lovely proposition that this stabilizer, defined this way, is just a subgroup of the group G. Okay, so let's look at a little example so that you can see what it looks like. Okay, so this one here involves the group G equal to the dihedral group of order 8, or the symmetries of the regular fourgon, the square here. So that consists of 4 rotations, okay, and also 4 reflections. And let's pick an element that's inside what D4 acts. So D4 acts on the whole plane, okay, and we'll just pick 1, 0. That's that point there, okay. And you can ask, well, which of these group elements, okay, these reflections and rotations, fix this point, okay? So here you've got 4 rotations. If you rotate anything other than the rotation by 0, the trivial rotation, you will move this point. Okay, so the only rotation that you have inside this stabilizer is the identity, okay, the identity map. What about reflections? Okay, so if you reflect about this vertical axis, of course that will move this point here. So the reflection is not the same as the original. If you reflect about either of the diagonal lines, of course you also move this point. But if you reflect about the horizontal line, the x-axis, then this point stays fixed. So the reflections which are inside the stabilizer is precisely this one here. And of course it's easy to see that these two form a subgroup of this. Okay, in fact it's all the powers of this, and since this is a reflection, it's square, it's just the identity. And that gives you the stabilizer in this example here. We can now present the wonderful and beautiful structure theorem for G-orbits. Okay, so let's suppose we have X as a G-set, and it's a G-orbit in the sense that it contains just a single G-orbit. Okay, so what that means, that basically it is of the form G dot X, where X is any element of big X. Okay, so that's the single G-orbit. Okay, so if you look the equivalence class determined by this G action, then they all form just one big equivalence class, which is the whole of X. Okay, so in this case we've picked this little X, and we can talk about its stabilizer, which is some subgroup of G. So we can form this set of cosets. Okay, this is a set of cosets of H, and this is a G set as well. And I claim that this X is isomorphic to this G set G mod H. Okay, so this is a really wonderful theorem, because a G set is what we use to describe a situation of symmetry, okay? And we know that any G set is a disjoint union of orbits. So in fact, we have the following corollary, that any G set is a disjoint union of, well, up to isomorphism, things of the form G mod H alpha, where H alpha is some subgroup of G, and these alphas of course can be different, okay? So that's the situation that we have. So we have a nice description for any G set. And the funny thing is that even though when we talk about symmetry, we need to talk about permutation representations, up to isomorphism, to study such a permutation representation, we just need the group G and also knowledge of all the subgroups as well. Okay, so we can define it internally in terms of the group G, what possible permutation representations that you can get, and they're given by things of this form and their disjoint unions. Okay, so now that we've stated the structure theorem, let's go ahead and show you how this proof works. Okay, so I just need to exhibit an isomorphism from, in this case we'll go from here to here, from this G set G mod H to this X. And the way it goes is as follows. Suppose I have this coset GH. So remember, this is the set of all products, little g times little h, where this little h ranges over all the elements of this subgroup H. And what I do is I send this element to G dot X. Okay? So the first thing that you have to check is actually that this is well defined. Okay, so why is that? Well, another way to write this GH is if you have any group element little h inside big H, and you look at the coset containing GH, okay, here, that's GH big H, that's the same as GH. So, of course, the thing you need to check is that it doesn't matter whether you use this little g or this GH in here, you get the same answer, okay? So then you need to check that that's well defined. And remember, this is essentially the H orbit of this element G, where the H action is the regular right regular action here, okay? So the ways that you can write out this K-set is precisely all the elements. The element that you can stick out here is precisely all the elements inside here. So they are the things, little g times little h, okay? So that's the thing that you need to check, okay? That when you change this to a different representative, so to speak, of this coset, so instead of this one here, g to gh, using this formula doesn't give you a different answer, okay? Which would be bad because they correspond to the same element here. So one element here should go to one element here, right? Okay, so let's have a look at that. gh.x, let's see what that is, okay? So by associativity is this g.h.x, and the key point here, and this is where the stabilizer is crucial here, is that h is in the stabilizer. So h.x is just x, this is just g.x. So it doesn't matter whether you have g here or gh here, you always get g.x as the final answer. And that gives you a well-defined map from here to here. And then to complete the theorem, all you need to do is to show that f is bijective. And that's a fairly easy exercise I'll leave for you. But I guess the most important thing is that where have we used the fact that this G-set is a single orbit? That's to show that this is surjective, okay? So what's the image of this map? It's all the little g.x's, as this little g varies over the whole group. Okay, big g.x is the set of all little g.x's. It's a set of all of these. So the image of this is a set of all of these, which is big g.x, that's the g orbit. And since we assumed big X is a single g orbit, then this is all of x. That's surjectivity. And injectivity corresponds to the fact that you've used the stabilizer here, okay, the full stabilizer, not just some elements which stabilize. And that gives you the proof of this theorem, and hence this corollary, okay? And hence you have a complete description of any G-set that you like, okay, in terms of these G-sets here, okay? So these are some like the atoms that you can use to build any G-set that you like. Okay, so let's look at a little simple example of what's going on, and we'll pick this same one that we had before. So we'll have G is the dihedral group of order 8, the symmetries of the regular foregon, symmetries of, say, this square here, okay? And what we did last time is we picked the element 1, 0. Here it is here. 1, 0. And we saw that the stabilizer for this was just the elements 1 and tau. Okay, this reflection about the x-axis there. Okay. Okay, so let's have a look at the orbit of this 1, 0. Okay, so all the group elements act on this 1, 0. Okay, so you have 4 rotations. The identity of rotation doesn't move it anywhere. You can rotate it 90 degrees via rho. That'll bring you up to here. So that's 0, 1. You can rotate it by another 90 degrees to get you over here. That's minus 1, 0, minus 1, 0. And then you can rotate it again down here. Okay, so that's the 4th point. The other thing you can do is you can reflect. Okay, so if you reflect this this way, of course that's a stabilizer, so it doesn't move this point. You can reflect about this diagonal, and that will send this point to here. You've already got that in the orbit. You can reflect about here to get this point, and you can reflect about this diagonal this way to get this point here. Okay, so the orbit consists of 4 points, and I've written them down here. Okay, so what does the theorem say? It says that this G orbit, okay, we can describe in this form as a G mod H. Okay, so what is the G mod H? It's this one here, G mod the stabilizer, that's 1 tau. Okay, so let's check that you believe that this is true. So firstly, remember, we had a theorem in the last video which tells you how many elements are inside here. Okay, so remember, what are the number of cosets of this subgroup inside here? Well, this is 8 elements, and this is 2 elements. So this is 8 divided by 2, which is 4 elements, which is the same as the number of elements here. Okay, so that at least makes it believable that there's an isomorphism. Okay, and let's see how that isomorphism works. So how does this work here? So group elements get sent to, well, you just let that group element act on that little element, in this case 1, 0. Okay, so 1 and tau fix this one, so this element here, 1, 0, corresponds to the subgroup 1 tau. Okay, so these fix this element, and this is one coset, is the group itself, the subgroup itself, 1 tau, and that gives you something here. Now if you let rho act on this element, you get up to here, right? So the coset containing rho, so that's the set rho and rho tau, that's going to be the coset, the element of this set of cosets corresponding to 0, 1. Okay? So rho is the rotation by 90 degrees, and rho tau is a reflection. Of course, it must be the reflection about this diagonal, which sends this point to this point. Okay, so that's another coset. And similarly, you can show that what is the coset corresponding to this one here is just the coset containing rho squared, the rotation by 180 degrees, and also the reflection in there is just a reflection about the vertical axis. And the final one is the coset containing the rotation in the clockwise direction by 90 degrees, and also the reflection about this diagonal. Okay, so that's your 1-1 correspondence between the two, and it's more than that, it's actually an isomorphism of G-sets. So it's compatible with the G action as well. So this shows you a nice example of this theorem in action. Okay, fantastic. We have a complete description of all G orbits, and hence by the orbit decomposition of all G-sets. And this description is just internal in terms of the group itself, G, and you just need to look at the various subgroups that can arise. But there's one thing that you might notice is a little bit funny here, okay? To write this out, X is isomorphic to GH. Where did the H come from? It comes from the stabilizer of some element X. And what was that element X? This element X is just any element inside this big X, okay? So there was some choice involved here, right? There's some choice involved, but in this, right, there's no choice involved to what that is, okay? So what happens if you change this choice, okay? Then they should be isomorphic, right? This theorem doesn't depend on what choice you have there, okay? So this is the warning, which is something that just happens with group actions that you need to be aware about, okay? So suppose X is some G set, okay, and you've picked a little x inside here, big X, and you have the stabilizer, H equals stabilizer of X. And let's suppose instead of picking this element here, you change it by something else in the G orbit. So you change it to G dot X. So let's suppose we have this G here, and you looked instead at G dot X, okay? So what's the stabilizer of G dot X, okay? Is it the same as the stabilizer of X, in which case this doesn't change? Well, this little warning tells you actually what happens, okay? The stabilizer of G dot X may not be the same as the original stabilizer of X, but it's related in a very strong way. It's going to be GHG inverse, which I hope, as the notation suggests to you, is G little h G inverse, the set of all these, as little h ranges all over the subgroup big H. Okay, so this is known as a conjugate of the subgroup H. Okay, it's a conjugate by G. Okay, because you can let the conjugation action act on the group, and then this is the conjugate of this H. And this is the stabilizer. So it changes in the set fashion. Now sometimes this could be the same as H, but sometimes it's going to be quite different as well. Okay. So for example, if you look at the stabilizer of this point here, okay, in this orbit, we could have picked the stabilizers of any of these points and said X is isomorphic to G mod that stabilizer. Stabilizer of this point is the identity, of course, but now the reflection you have is not the reflection about this axis, it's a reflection about this axis instead. Okay. If you put this point here, the stabilizer is the same. Okay, it's still the identity and the reflection about this horizontal x-axis. But sometimes it can change and sometimes it won't. But the way it will change is in a very set way. Okay, so that means that, well, when you write this out, X is isomorphic to G mod H. This H is not unique. Okay, you can change it by changing X. And that shows you that, well, if you change X to G dot X, okay, in one case you get G mod H, in the other case you get G mod GHG inverse. So of course, since isomorphism is an equivalence relation, okay, then X, so that's quite easy to see, okay, then you find that those two G mods, okay, so G mod H and G mod GHG inverse, these are isomorphic as G sets. Okay, so of course A implies B by the theorem, let's show why A is true. And it's a nice little calculation too, okay? So we just want to compute what is this stabilizer. And by definition, it's all the elements in the group K inside big G, such that when you let K act on G dot X, so that's the same as KG dot X, it doesn't change this G dot X, so that equals G dot X. So let's examine this condition in greater detail. KG dot X equals G dot X. It's an equation, and we just examine it. Okay, so it's equality of two things inside big X. We can permute use a permutation of the elements of X. That's going to be left multiplication by G inverse. And so when we apply that to this equation, we get an equivalent equation. So this is G inverse KG dot X, that's this one here, equals G inverse of this, G inverse dot G dot X, which is G inverse G dot X. This is the same as 1 dot X, which is just the same as X. So in other words, this equation here, you can basically move the G over to the other side to say it's equivalent to G inverse KG dot X is equal to X. In other words, this element G inverse KG, when you apply to X, it stabilizes X. So that just means that this element G inverse KG is inside the stabilizer of X, which is just H. Okay, so it's just inside H. And I hope you can see, well, what were we interested in? Well, we're interested in all the K's. What does it mean for K to be inside the stabilizer? K being inside the stabilizer just means this equation, and here we can solve for K to say that that just means that K is where you put the G to over here, and on the right you multiply by G inverse to say that that just means that K is inside GHG inverse. And that's precisely what we have here, okay? So the condition to be in the stabilizer is just to be inside here. So in other words, this set is equal to this set here. And that shows you how the stabilizer changes when you replace X with G dot X. I hope you enjoyed this adventure in pure mathematics.